All right, so starting section 9.5, we're going to talk about hypothesis tests for proportions. Okay. So a hypothesis test involving proportions or population proportions is a binomial experiment. Only going to have two outcomes. You can have successes or failures. Okay. Successes are going to be obviously the thing that we are trying to test. Okay, that proportion. That's the thing we're usually interested in. Okay. If you remember from binomial experiments, our mean is n times p. Okay, n being the sample size, and p being the proportion. Okay, and then the population standard deviation is the square root of NPQ. Okay, and we talked about that stuff chapter 8 at some point. Okay, it was 8.4 or something like that. Okay, so in order to use a z distribution, because that's what we're going to try to go to now. Okay, so we've used a z distribution for means, with sigma being unknown, with sigma being known, with sigma being known, and then we used a t distribution for sigma being unknown. Now we're going to go to with proportions using the z again. So it's important when we go through these questions to identify now what is the key phrase. Is the key phrase averages or means, or is the key phrase proportion? Okay, because if it's average or mean, then you have to decide z test or t test based off of the population standard deviation and the knowledge about that. If it talks about proportions, you're going to only right now use the z distribution. Okay, so in order to use the z distribution, so that the binomial distribution is approximated by the normal distribution, we need the following things to be true. We need the sample size times the probability of a success, okay, or the proportion that is aligned with ultimately what we're interested in. That has to be greater than or equal to 5. And then n times q, which is q is a failure. Okay, that's the probability of a failure. That has to be greater or equal to 5 as well. We did the same thing when we did confidence intervals with proportions previously. Okay. Still going to have a similar format to finding our test statistic. Okay. Basically, it's your observed mean minus the hypothesized mean divided by then the standard error. Okay, which is that formula there that you see at the bottom where it says z equals p hat minus p. So p hat is the sample proportion. Okay, and then we have divided by the square root of p times q divided by n. Okay, and you see there to the right that p hat, how we find p hat, it's x divided by n, where x is the amount of successes divided by n, which is then the total number of objects in your sample. Okay, this should not be, if we understood the t-test and the z-test so far, okay, this is just ultimately using a new formula to get a test statistic. But once we have that, we use exactly the same methodologies that we used in the previous testing to make decisions on the null hypothesis. Okay, so you're still going to look at critical values and find critical values the same way. You're still going to find and use p-values and use p-values in the same way. It's just the way that we garner the z is a little bit different. Okay, but it's really my hope is that structurally we see that it's really the same. It's we see there at the bottom it says test value is equal to the observed value, which is our sample proportion in this case, minus the expected value, which is what we are saying is the population proportion. Okay, and then you divide that by your standard error. And that's what we've been doing so far with all of our tests. Okay, that's the kind of the general formula that all our test statistics follow. Okay, so if we can remember those, and I guess we don't even have to remember them. We'll have them in front of us, those formulas for the z working with the proportion. We fill those components in. Once we get that test value back, then we can compare it to critical values or p-values, however we decide to do it. Is that okay? All right. So jump right into doing some examples here. This one says a research center claims that 25% of college graduates think a college degree is not worth the cost. Okay, so you decide to test this claim and ask a random sample of 200 college graduates whether they think a college degree is not worth the cost. Of the observed, 21 replied yes, or 21% replied yes. It says at alpha equaling 10%, is there enough evidence to reject the claim? Okay, so just like everything else, we have to write our hypotheses first, identify the claim. So we're going to have our null hypothesis and our alternative hypothesis. So the alternative hypothesis, well, let's phrase it this way. The null hypothesis is what is being accepted, right? Okay, it's what we have already established. Okay, here it says a research center claims that 25% of college graduates think a degree is not worth the cost. Throughout there, this is one that I think is a little bit different than the phrasings that we've seen before. If I look at that phrasing, and then I look at another phrase that deals with our situation, it says down here, of those surveyed, 21% replied yes. So one of those values, either 21% or 25%, is the p hat, and the other one then is p. Okay. I'm just going to tell you 25% here is what we are going to accept, or what we are accepting as the population proportion. Does that make sense? The 21, that came from surveyed people, right? So the 21, we could not survey the entire population, so that's a sample proportion. Does that make sense, everybody? Okay. So if we look at the formulas up above, p hat is x over n. Okay. When it says 21% replied yes, they're telling you already what x divided by n was. Okay. They've already changed it to a percentage for us. Okay. Maybe it was 21 out of 100. Could have been 42 out of 200, whatever. Okay. But that's the idea there. Now, are we talking about means anymore? Does it say means anywhere throughout this problem? Or averages? No. What we're talking about, because they give percentages, they're talking about a certain portion of the whole. Then we're talking now about proportions. So we got to use P as our parameter, okay? And then down here, we'll also use P. So it says, when it reads this, okay, it says a research center claims that 25% of college graduates think a college degree is not worth the cost, okay? So we're saying that is 25%, okay? Or I should write it as a decimal, 0.25. Okay. Now, it says you decide to test the claim and ask a random sample of 200 college graduates whether they think a college degree is not worth the cost. Okay. Of those surveyed, 21% replied yes. Okay. At 10%, is there enough evidence to reject the claim? Okay. So when they say is not worth the cost, we're looking at that there. Okay? Okay, now we're going to run through and figure out what our critical values are. So our critical values, okay, this is good. We're going to use a Z distribution. So we're looking at, this is a two-tailed test now. Okay, so alpha is going to be broken up into two tails. Okay, so we should have in this area, in this region, should be an area of 0.05, and that area should be 0.05. Does that make sense? So the T values then that go with alpha over 2, or Z values, sorry. Z values that go with alpha over 2. We go equals, okay, it's a normal curve, it's a Z distribution, so normal.dist, okay, and that's the wrong one. I always get them confused, and this is why I like Excel. I get the normal distribution and the inverse norm confused on which one's going to spit back what I'm looking for. Does that make sense? If I type this one in, and I know a lot of people are on the same page with this, they keep asking, which one do I use? Well, think about this. When they type this in, okay, they ask you for X, okay, and you can kind of view that X, it's what it is a standard deviation, but think about your curve. Put your curve on the Cartesian plane. The X, if I put my normal curve on the XY axis, okay, the X value is the standard deviations across the bottom. Does that make sense? That's what we're looking for, is it not? Okay, we're looking for, think about this, if we insert, if we put our y-axis, so our y-axis would go right there, and our x-axis would go right there. Does that make sense? Okay. We're looking for essentially that x value and that x value. Okay. We don't know those, so when I type this in and they ask it for x, well, I don't know that. That's what I'm looking for. So I can't use that command. I have to use this one. And now it says right here that I'm looking for a probability, right? Okay. So I think using Excel, it's more intuitive if I get confused on what command I'm using. It provides me the conditions that need to be met, that need to be typed in for it to calculate. Okay. So we're looking at 0.05 here is the probability. The mean is always 0. The standard deviation is always 1. That gives me negative 1.64. Negative 1.64. So that value right here, okay, is a z-score of negative 1.64. And this one here is a z-score of positive 1.64. Okay? Because the curve is symmetric, I don't need to do that norm inverse twice to get the positive 1.64. Is that all right, everybody? Okay, so that's going to be our tool to make our decision. Okay, and now all we have to do is determine what is the test statistic. Okay, so Z is equal to p hat minus p divided by the square root of pq over n. Okay? Now, when we evaluate that, okay, p hat, remember p hat is the sample proportion. Okay? So that was the 21% that replied yes. So it's going to be 0.21 minus then p, which was identified in the null hypothesis as 0.25. And then we're going to divide that by, okay, PQ over root N. Okay. Now, when we do this, and then I should have maybe written this in somewhere, P is the population proportion, right? Okay, that's the 0.25. Okay. Q is the what to that? We remember? The complement. Okay, so we'll put 0.25 times 0.75 there. 0.25 times 0.75, and then root n. Okay, so I do need to know, even though I didn't tell you how many people said yes, I told you that as a percentage, I still do need to know how many people were sampled, right? In this case, there were 200 people sampled. Okay. So we could have, in this story, they could have said, 200 college graduates were sampled, 42 of them agreed yes, okay? So that would be equivalent to the 21%, right? Okay. So we can evaluate that. We can type that into our calculator. So we'll do that. So 0.21 minus 0.25. Okay, and we get negative 1.3. Negative 1.3. And that is our test statistic. Okay, so then we go to our tool that we're going to use, our curve that we have developed to decide whether we reject or not reject. And we're going to put that Z distribution that we just found from our data, and we're going to place it accordingly to these rejection regions. So negative 1.31 is going to be the left of 0, but does it get far enough into the rejection? Or it's going to stop short, isn't it? So that right there is going to tell me that I do what with the null hypothesis. What the red region was the rejection region, right? Okay. Did this blue value that came from our data, did it fall in the rejection region? No. So can I reject? No, we would fail to reject. So this is what I would write. This is how you would stay, hopefully, consistent when Math Excel asks you to do drop-down windows and stuff like that for your summary. We would say fail to reject H sub 0, okay, which is the null hypothesis. Let's write this way. Okay, fail to reject the null hypothesis. Okay, there is. Okay, so if I fail to reject it, that means because we set off assuming this was true, right? That was the accepted truth. Okay. We failed to reject it, so it stays or remains the accepted truth. Does that make sense? Okay. So we fail to reject the null hypothesis. There is then evidence to support the claim, because the null hypothesis is the claim, okay, that 25% of grads do not think college is worth the cost. Okay? Fail to reject the null hypothesis. There is evidence to support the claim that 25% of grads do not think college is worth the cost. That kind of make sense? Okay? So basically what we're saying there is that, you know, we've got this 25%. Maybe they've done a previous study the year before, whatever, and gave this 25%. Okay? What we're saying then, when we sample 200 people and they say 21%, that's not far enough away from 25% to say that no, the population is not 25%, or the population does not believe that that college is not worth the cost. The population that is in agreement with that is not greater than or less than 25% in this case. Does that make sense? Okay. And in this problem, we think about the alternative hypothesis being a not equal to, because the structure of the problem doesn't really say that, you know, maybe when we say it's not worth the cost, does that mean that college is, or the degree is worth more, or the degree is worth less? Does that kind of make sense? It doesn't tell you what side of the spectrum to sit on when they say not worth the cost. Okay. Does that make sense? So we'll do another example. But do you see that the structure here is exactly the same as what we've been doing? Just a different formula to test our data. Okay, it says you interview a random sample of 50 adults. The result of the survey show that 48% of the adults said they were more likely to buy a product when there are free samples. So that alpha being 5%, can you reject the claim that at least 52% of adults are more likely to buy a product when there are free samples? Okay, so let's why don't you guys take a minute here and see from this. We know it's going to be proportions, but see if you can come up with what you think your null hypotheses and your alternative hypotheses should look like, and then identify which one should be the claim. When you read, I think this one's kind of backwards. Just get the hypotheses written here. It says you interview, so it starts talking right away about your sample, right? Okay. It says the results of the survey, so still talking about our sample or survey. Okay. And then it says at 5%, so we've got that. That's our alpha. It says, can you reject the claim that at least 52% of adults are more likely to buy a product when there are free samples? When we say at least, what does that mean? What does at least mean? Bare minimum, right? I'm setting a floor there. Okay. But when it says at least, can I be standing on that floor? Can I be at 52%? So there's equality there, right? Okay. So we're saying that when we set that floor, that the proportion, the population proportion, when it's at least 52%, that means the floor is the bottom value, so we could be greater than the floor. So we'd be saying that. Is that okay with everybody? 0.52 as your null hypothesis, and that would be our claim in this situation. That says it right there. So then the alternative hypothesis, what would be the complement of this? less than 0.52, right? If we draw our Z distribution, okay, what kind of tail is this? A left tail, okay? So the left tail. So in this left tail right here, we want 5% of our area, okay? So that's alpha equaling 0.05 there. So this Z-score that's attached to that alpha, okay, is it the same as the value that was in the previous problem? Yeah, it's negative 1.64. All right, so now all we have to do is run through and figure out our Z. So Z is P hat minus P, okay, over PQ divided by N, the square root of that. Okay, so P hat, that is your sample proportion. Okay, sample proportion. So in our sample, it says you interview a random sample of 50 adults. The results of the survey show that 48% of the adults said they were more likely to buy a product when there are free samples. So P hat here is what number? .48. P is 0.52. Okay. So then we'll divide by the square root of 0.52 times Q, which is in this case going to be 0.48, right? Okay. Divided then by root N, or not, sorry, not root N, just N, which would be 50. So, Desmos out. This turns into 0.48. 52. 52. 48. And then 50. We're at negative 0.566. So that Z value then is going to fall, if 0 is right there, negative 0.566. It's probably about right there. So what do we do? Fail to reject, right? Fail to reject, okay? There is evidence to support the claim. Okay, because remember when initially we accept that, and if we fail to reject it, that means we continue to accept it, which would then mean that there's evidence for it. Is that right? What if I want to use p-values, Chuck? Can I use p-values? Huh? For this. Let's think about this. Well, the area, so the p-value is the area that is cumulative from the left up to our test statistic. That, so it'd be that blue area there. Does that make sense? Is that blue area, is your p-value going to be greater than alpha? Yes. And we remember from previous sections that the p-value is greater, that means you fail to reject. Okay? So let's go ahead and take this negative 0.566 and run through Excel and see if we can find what the p-value is. Okay? So in this case, this is the one where I do need to use the norm dot dist, because now it asks for an x value. Well, we currently have that x value. That x value is ultimately this z-score of negative 0.566. So plug that in, negative 0.566. Okay. Standard deviation, 0. Mean, 0. Standard deviation, 1. Cumulative, yes. Type in true. It gives me that number right there, 0.285. So we're saying that this blue area is 0.285. Alpha was 0.05. So we're seeing that that p-value of 0.285 is greater than 0.05. So again, we would fail to reject. So you can use in all of these, just like what we've done before, you can use critical values or you can use p-values. Okay? If it was up to you, use whatever you're most comfortable with. Okay? But Math Excels, they're going to jockey back and forth between both. Okay? I think a lot of them on Math Excel, for whatever reason, this section are critical values, but they might throw in a p-value here and there. Okay, so just be on the lookout for that. Is that something we can do? All right. I will. It's already open, but I'll extend it. But there's a proportions assignment on Math Excel. Should not be. And my hope is right now, guys, that we've gotten to the point. We've been doing the hypothesis testing now for pretty close to a month. That we understand the nature, the structure, and really now as we move on, the only thing that's going to change are the formulas for the test statistics. Okay, and once we calculate those test statistics, we still address the problem the same way as we have other hypothesis testings. Okay. Looking forward, like I said, next week we're going to be looking at differences between means, differences between proportions. So what happens is right now we've been only looking at one sample, right, or one group. Okay. Next week it's going to start being maybe a little bit more applicable because we can now start thinking about, okay, we want to test whether a medicine was impactful versus a placebo. Okay. So we'll have group 1 and group 2. We'll have the results from group 1 and group 2, and then we can say, okay, are their averages, their means, their proportions, whatever we're interested in, are they different? And if they are different, then was it the medication that was the reason or not? Okay, so that's kind of where we're going to go with this stuff next week. Okay, and then what that does is Excel has, we talked about this yesterday, Excel has a lot of built-in functions, okay, that will allow us to generate p-values and stuff like that just by inserting our data. The 2 sample tests, Excel is built targeting those, okay, so we might be able to address some of that stuff. I also, I told 7th period, I don't know if I told you guys this yesterday, I would like to eventually come back to this stuff that we're doing now, and maybe build some Excel sheets collectively with you guys so that we could just insert our data and hit enter, and it automatically runs through everything, and we can conditionally format it to just say reject or not reject. It gives us the answer almost instantaneously. Does that make sense? And all we have to do is input our data, because that's really what happens when we are using statistical packages. I'd like to be able to use